Last page in this unit, and then we'll do some problems. We'll start with the combined gas law. Turn to table T in your reference tables. And you should find, with gases, combined gas law. PV over T, pressure, volume, temperature 1, equals pressure and volume, temperature 2. Before we get started, let me just remind you right here in short, PV over T, whenever you have variables side by side, like P and V here, they are inversely related. Which means if one increases, the other decreases. Whenever you have variables directly on top of each other, like V over T and P over T, they are directly related. Which means if one increases, the other increases. If one decreases, the other decreases. That's good to keep in mind. Now, about this formula. Whenever you do a gas law problem, what you should do is look for what is constant in the problem, what remains the same, and just omit it from the formula. So if you come across a problem, they tell you temperature is constant, as in the case here, then you're not going to use temperature in the formula. So let me just erase this here so I can scroll down. So if they tell you the temperature is constant, you're not going to use temperature. So your formula becomes PV equals PV, again, initial, final. So at constant temperature, you're left with volume and pressure, and they're inversely related to each other. This is known as Boyle's law. Probably learned it that way when it was developed in school. All right, we have an inverse relationship. One is decreasing, the other one's increasing. Nice demonstration of that is if you have a container with a movable top, a piston in other words. And if you decrease the volume on this gas, the pressure of that gas will increase. The reason for that is because the less space there is, the more collisions there are going to be between the gas molecules. And pressure is directly related to that. The pressure of a gas is due to the number of collisions per second of those gas molecules against the walls of the container. So if you double the volume, you're going to half the pressure. If you half the volume, you'll double the pressure. They're inversely related. If you 2 to 1, 1, you will 1/2 the other. You're going to do a flip. And of course the same applies for if you triple one, or if you, let's say you 1/3 the volume, then you're going to triple the pressure. They're inversely related, so you'll do a flip with this. And then graphically what this looks like, volume versus pressure or pressure versus volume, you end up with a curve like this. This is an inverse relationship. So you'll never hit 0 here or 0 there. It's not a straight line, it's a curve. Again, an inverse relationship, Boyle's law, but they won't ask you that. You won't have to know the names of these laws. Now, starting with the combined gas law, they tell you the pressure is constant, then your PV over T becomes a V over T equals V over T. And what you have again is a direct relationship. Meaning if you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. Or if you double one, you double the other. If you triple one, you triple the other. Whatever happens to one, happens to the other. The demonstration I did in class was, I took a deflated balloon and I strapped it to the mouth of a flask, and I heated the air inside the flask, and the balloon filled with air. It inflated. It wasn't as dramatic, but it certainly demonstrated that if you increase the temperature of that gas, you'll increase its volume under constant pressure. And the graph of this direct relationship, V versus T, is a direct line straight up. Notice I wrote Kelvin temperature. Even if it were in Celsius, it would be straight up, but it would cross the curve somewhere up here instead of through the axis. I wrote Kelvin temperature to remind you that whenever you do calculations with this law, which happens to be called Charles's law, you must first convert to Kelvin. That's really important. Otherwise you'll get the wrong answer. Don't convert to Kelvin after you do the math. Convert to Kelvin before you do the math. And finally, the other possibility is if they tell you that the volume is constant. In which case they might say the gas is confined in a rigid container. Rigid means non-flexible. It's not a balloon. So instead of placing a balloon on the mouth of the flask, you cork it. Now this glass container is rigid, not flexible. So what's going to happen there is that those molecules, as you heat them up, they're going to move faster and faster and collide with each other more and more with greater force, and so the pressure inside here will increase, and there's only so much that that cork can withstand, and finally the cork pops out. Again, increase one, increase the other. Double one, double the other. Triple one, triple the other. Whatever you do to one, you do to the other. And that's what happens in a rigid container when you have constant volume. This is called Gay-Lussac's law. But again, that's not important. Again, the graph is going to be linear going straight up. If you use Kelvin temperature, it will go through the theoretical 0 Kelvin, which we all know we never reach. That's a direct relationship. So we end up with an inverse and two directs. If you come across a problem in which you feel they haven't given you enough data, it's probably because you've overlooked the mention of STP. STP stands for standard temperature and pressure. You'll find the values of STP in Table A of your reference tables. Standard temperature is 273 Kelvin, and 1 atmosphere pressure would be standard pressure, all 101.3 kPa's. I hesitate to put in 0 degrees Celsius here, which is standard temperature in Celsius, because I'm afraid you're going to use Celsius in your calculations. That is, you're going to forget to convert to Kelvin. So please don't do that. And wrapping up this page, and by the way, if nothing is constant, you're going to have to use the combined gas law, all of the variables, and the math there is a little bit more difficult. Wrapping it up, we have Avogadro's law. Avogadro's law is very simple. What Avogadro stated was if you have two gases, two different gases, gas A and gas B, it doesn't matter what gases they are, if they have the same volumes and the same temperatures and the same pressures, then they must have the same number of molecules, whatever that number happens to be. All right, we'll see a question like that when we do some problems. And finally, at the bottom of this page, we have the ideal gas theory. Ideal gases, an ideal gas is a gas that behaves best, that obeys the gas laws that we just mentioned. So in other words, your calculations on paper will be very close to your actual measurements in the lab. Now, the two most ideal gases are helium and hydrogen. The reason why helium and hydrogen are the most ideal gases is because they are the smallest. So in terms of the molecules, the smaller the molecular size, it turns out the weaker the attractive forces between the molecules. And that's good if we want our substance to behave as a gas, because those molecules will be far away from each other. So we have a greater intermolecular distance. And that substance will act more like a gas than it does a liquid. Therefore, the more ideal the behavior. Now, in terms of the conditions that you can manipulate, it turns out the higher the temperature and/or, which means you're controlling both factors here, it's not one leading to another, the higher the temperature and/or the lower the pressure, the more ideal a gas will behave. Here's an easy way to remember that for the conditions. Hot lips, more ideal. Hot, high temperature, lips, low pressure, more ideal. And if you want to bring in the molecules themselves, a student of mine came up with this one, which was smart males will attract hot lips. All right, smart males will attract hot lips. It's silly, but it works. Smart males has to do with small molecules, weak attractions, and then again the hot lips, as you know. So S, small, M, molecules, W, weak attractions. And hot lips, high temperature, low pressure. So that's putting it all together. And that might help you to remember it. All right, congratulations. You've come to the end of the longest unit. And let's do some problems to wrap it up. And of course, what you should do is go over these notes again and do another set of problems and another set of problems. Of course, the more problems you do, the more ingrained these notes will become. And this is really all you need as far as this unit is concerned. These notes were made by studying Regents exams and seeing what kinds of questions they ask. And this is the material that's tested. Okay, I'll see you there.